Okay, there is a great note in the margin of that page, and you need the results of that note. It's going to come into play. The squeeze theorem I only use like once or twice, but the note that's right there by it we're going to use a bunch of times. If you remember the squeeze theorem from Calc 1 by any chance? Oh, you do? Oh, hooray. Do you remember what it was packed in with?
Sine theta divided by theta.
Yes, it was. Oh my gosh, how can you remember that? When we did the limit of sine theta over theta as theta goes to 0, back then we didn't have L'Hopital's rule. So what we had to do is make two functions around that function and show that their limits went to 1, and therefore the limit of sine theta over theta went to 1. That was for functions. This is the same theorem, only now it's for the little dots instead of for continuous functions. So it should be relatively appealing to you. Not planning to dwell on it too much, but you need to know that it exists. Now the little note that's in the margin talks about this, the limit, as n approaches infinity of k to the n over n factorial equals 0. So the factorial, factorial function. I got both of these things. I've got this and I've got this. Factorial function grows faster than any exponential function. Example 5 suggests something about the rate at which n factorial increases. Figure 9.2 suggests both 1/2 to the n and 1 over n factorial approach 0. Yeah, we know that. But 1 over n factorial approaches 0 so much faster than 1 over 2 to the n that the limit of 1 over n factorial over 1 over 2 to the n, that's the statement you need to have some feeling for. And it's not always going to be the number 2, but the concept is the same. The exponential in the numerator with a factorial down in the denominator is going to end up going to 0 because that factorial grows so fast. You know, I'm always talking about the bottom blowing up. Well, factorials really blow up. Okay, so they grow very fast. Okay, then a little piece on some new words. Monotonic, which we've never used before, and bounded above and bounded below. But you've done a little bit of that with your calculator, so that might not be too bad. A sequence is monotonic A sequence is monotonic if it's non-decreasing or non-increasing. Now the words you all know are increasing and decreasing. What's different? Okay, you got the word non, but what's different about being non-decreasing versus being increasing?
Staying the same?
Yes, the trouble is the constant parts of that, and that's the little equals to in this thing. If this thing was really increasing, we would have that A1 would be less than A2 is less than A3. And the picture in your head goes like this, I hope, when you're thinking of increasing. But with sequences, it doesn't matter if some of them end up being the same value, as long as we're always looking long term with sequences. So it's not the here and now that I'm that concerned with, it's what about out there. So as long as in the long run I'm increasing, or in the long run I'm decreasing, the sequence is called monotonic. And some values, it's all right if they're equal. Now, why do we care about that? Bounded, I need first, bounded above.
If it's a constant function just throughout the whole time and it doesn't increase or decrease, it's still monotonic?
Hang on, because that's even better. That's what we're going to actually use to do the work. The fact that we know increasing and decreasing. If I told you that a sequence is bounded above, I'm telling you that there is some number greater than or equal to all the terms. If it's bounded below, there's some number less than or equal to all the other terms. So for example, if you graphed a sequence